if we want to differentiate functions with higher powers of x, for example x to the power of 3 or x to the power of 8, and we use the differentiation from first principles formula to do that, it will be quite difficult because when I try to do x cubed, I will have x cubed here would have been my function, and x plus h for my function would have been x plus h cubed, and then I would have to multiply that out. Think about what that might be for x to the power of 8. So this would have been x plus h to the power of 8, take away x to the power of 8 over h. That would be quite difficult to do, so we need to find a general formula that helps us do that. So let's see what happens when we try and do f of x is equal to x to the power of n. So any power n, let's try and apply this formula to f of x is equal to x to the power of n and see if we can get a formula to differentiate any of these functions. So if we start by saying, okay, we're going to take the limit as h goes to 0. So x to f of x plus h. So if I put x plus h here, this would be x plus h in brackets to the power of n. So I will have x plus h to the power of n, and take away f of x, or take away just x to the power of n over h. Now, if you remember the binomial theorem, this can be expanded using the binomial theorem, and that's what I'm going to try and do. And then we'll see if we can find any sort of pattern. So this then becomes limit h to the 0. So if I use the binomial expansion here, the first coefficient I'm going to find by doing n choose 0. So I'm going to have n choose 0. And I'm going to have x to the power of n and h to the power of 0. Remember, h to the power of 0 is 1. N choose 0 is also 1. Let's carry on. Next value would be n choose 1. X to the power of n minus 1 and h to the power of 1. And the next value, n choose 2. X to the power of n take away 2 and h to the power of 2. And I'll finish it off now. And if I have, for example, n choose n and x to the power of 0 and h to the power of n, so this sort of goes from the first one to the last one, and I've skipped some in the middle. So that's the expansion of x plus h to the n. And now I need to say take away x to the n here. So I'll actually do that in a different color. So I'll say this bit I'm going to do in blue. So take away x to the power of n all over h. Now if you have a look, the h appears in all of these. This is h to the 0, so this will become 1, but the h is in all of these. And then I have one thing here without h. This actually will cancel out with this first one. So if I simplify some of these, let's see what I get. So this was h to 0, so limit h goes to 0. N choose 1 is just 1. X to the n is x to the n, and h to the 0 is also 1. So this is just x to the n. So I will have x to the n plus n choose 1. This is just n. And then I have x to the n minus 1 and h1. So I will have 1. So I will have n x to the n minus 1 and h plus, now these ones will start getting a little bit more difficult and I'll need to use fractions for them. So I'm going to keep this one as it is. So I will have n to x to the n take away 2 and h2. And again, this last one, I will have x to the 0 is just 1. N choose n is also 1. So this last one would be h to the n. So plus h to the n. Okay, and remember, all of these middle terms will have some power of h that is larger than h to the power of 2, and it will have some power of x that's more than x to the power of 0. And here I will have some other coefficient as well. And then the last term becomes h to the n. Now, I need to take away the xn, like I did here, and like it tells me to do here. Take away f of x, and f of x is x to the n. Now, if I divide this by h now, and see what I have. So here now, I can see that this x to the n, I can cancel with this x to the n. So I've got x to the n, and I've got take away x to the n. And this h will cancel at least one h from each of these terms. So this is h to the 1. That will just cancel that one out and leave me with that. That will cancel h squared to become h. It will cancel h to the n to become h to the n minus 1. Okay, so that's the next thing that I'm going to write. So I'll have limit as h goes to 0. So remember, x to the n will cancel with this one. So I'm just going to leave that out now. I'll write n x to the n minus 1 h plus n choose 2 x to the n minus 2 h to the 2 plus, and then h to the n all over h. Okay, so this time I'm going to start cancelling down. So remember, a h will cancel from every term, so these first two and everything in the middle and this last one, and that will reduce my fraction. Okay, so let's see what I get when I do that. So limit. Okay, so this h will just cancel that one, and I'm going to be left with n x to the n minus 1 plus n choose 2 x to the n minus 2, and this h squared, when I cancel down with this one, will just give me h to the 1, or just h. And this h can cancel down a h from every term here, and when it cancels down a h from this last term, this becomes h to the n minus 1. Now if I try and evaluate my limit, I can see that as h tends to infinity, it doesn't affect this one. It does affect this one, okay, because as h tends to 0, this is. So as h tends to 0, it doesn't affect this one, because there's no h here. This one, it does affect, because as h tends to 0, this whole thing will become 0, because h will get closer and closer to 0, and this will be 0. It affects every term in between, because there will be higher powers of h here, like h squared, h cubed, and h tending to 0 will make all of those terms 0 as well. And this last term will also become 0. So all I'm going to be left with is just this one. So this here, as h tends to 0, gives me n x to the n minus 1, like that. Okay, so we can see that when we try to differentiate fx equals x to the n, this is our result. So what we've been able to do is we've looked at the function x to the power of n, and we've seen that when you differentiate it, we get n times x to the n minus 1. Let's apply this to the functions that we had before. So we had gx is equal to x cubed. So I can see that for this function, n is 3, and the n comes here. So let me think about what the differentiation would be. So g dash x is going to be equal to, so the n is 3, so 3 comes in front of the x, and then I have to do 3 take away 1, and that's my power. So I will have 3 here, and x to the power of 3 take away 1, and then this I know will become 3 and then x squared, because 3 take away 1 is x squared. If I look at my other one, hx remember this one, x to the power of 8, this would have been a very difficult thing to multiply out, but because we used the general power n, we've been able to find a general formula to differentiate this. So when I differentiate this, it's very easy for me now. N is 8, so I have 8x and then 8 take away 1, and then this then becomes 8x to the 7. Okay, so now we're able to differentiate higher powers of x, like x cubed, x to the power of 8, very easily because we have this formula. I also want to show you a new notation. So if it was written y equals x to the power of n, when I differentiate that, I write dy over dx equals n x to the n minus 1, like that. Okay, so suppose y was equal to x cubed. When I differentiate that one, I will get dy over dx is equal to 3x squared. Or if y was equal to x to the power of 8, this becomes dy over dx equals 8x to the 7. So when you differentiate a formula like y equals x cubed, we write that dy over dx. This is not a fraction at the moment, this is just a notation, so dy over dx is equal to 3x squared. Now here are some questions for you to practice. So find dy over dx, the formula is given here for all of these functions, and then find the gradient function for this function here.